So this will be online.
Yeah.
So next, manage you are able to speak on adaptive token weighted differential privacy for LLMs. Not all tokens require equal protection. Unfortunately, he couldn't join each person due to some visa issues again. So they're going to present their work virtually.
Okay, good. Yeah.
Manjiang, you got 25 minutes, and please try to stop within 20 minutes, then you get some time to answer the questions from the audience.
Okay, good. Can everybody see my screen?
Yeah, hopefully.
Okay, good. Hi everyone. Thanks for coming. Today I will talk about adaptive token-weighted differential privacy for large language models. The core idea is that not all tokens need equal protection. This is joint work with colleagues at the University of Queensland and the Institute of Science Tokyo. So at the beginning, let's start with the problem and the motivation behind the token-aware privacy. Before diving into the method, let me quickly show why privacy matters in practice. Here on the left, you can see a clear example of how large language model can memorize training data. In this case, GPT-2 was just given only a short prefix as input, just a few words, but the model then reproduced a piece of text that looks like a real-world record containing names, addresses, phone numbers, and even email details. This shows that prompting alone can sometimes elicit verbatim personal information from a model, which is a serious privacy concern. And on the right, we see a table summarizing how much different large language model families are memorized. For example, Llama, Falcon, Mistral, and GPT models all show non-trivial percentages of memorized tokens. Even though the percentages look small, the absolute number of memorized sequences is huge. This means memorization is not just a rare edge case, but a systematic behavior across large-scale models. From the evidence we just saw, differential privacy naturally becomes an impossible way to protect the large language model. Record level differential privacy with clipping and Gaussian noise gives strong and principal guarantees. But there's still a problem. Traditional differential privacy treats all tokens the same, even though not all tokens are equally sensitive. This brings us to this idea of token-aware privacy. Actually, in practice, sensitive tokens are sparse. Think about names, phone numbers, or IDs. They are rare compared to the majority of common words. However, uniform DPSGD adds the same amount of noise to every token. This wastes privacy budget on non-sensitive token, and at the same time reduce model utility. The example on the right shows a medical record. Only a few tokens like a patient name or contact details are truly sensitive, yet uniform differential privacy still distorts every part of the sentence. This makes the training less efficient. So spend the differential privacy budget where it matters most, and that's the motivation for our method. Recent work has also realized that we should not add the same amount of noise across the entire dataset. Instead, noise should be allocated differently depending on sensitivity. You can see the idea across several lines of work, organized in the table on the slides by pipeline and by the unit of selectivity. The first one is ANA, which is adaptive noise allocation. The idea is that a different parameter in transformer model contribute unequally to privacy risk and model performance. They think less important parameter get more noise. It can strengthen privacy. This target allocation improves accuracy under the same privacy budget, narrowing the gap between private and non-private fine-tuning. And the second one is GFT, which is just fine-tuning twice. The motivation is that sensitive token in text are sparse, so we don't need to protect the entire sentence. They use two phases. The first phase is the redirected fine-tuning. They train the model on the data where sensitive tokens are masked or removed, so the model learns domain patterns without privacy risk. The second phase is the private fine-tuning. Then they just fine-tuning again on the original data with DPSGD, focusing noise on the sensitive parts. And on the third approach is ADP, which is adaptive differential privacy. The key assumption here is that they think sensitive information tends to be rare in text. So ADP estimates that probability that a sequence contains privacy using perplexity from a large language model. Higher perplexity means rare text and therefore more likely to be sensitive. During training, the method just adjusted the noise and magnitude per batch based on the average privacy probability. But it's important to note that none of these methods truly achieve token level privacy protection. In contrast, our method, which is adaptive token level differential privacy, goes deeper. We emphasize sensitive tokens inside each record and apply noise in token weighted way. Overall, our method makes three contributions. The first one is selective token weighted DPSGD. So we just reweight per record gradient contributions by assigning different weights to different token, providing stronger protection for sensitive information while causing minimal impact on existing model performance. The second one is the tiered privacy detector with light verification. We use multi-layer detector for personal identifiable information and contextual cues with optional one person human audit and large language model cross-check to fix edge cases and minimize missed sensitive content. The third one is lightweight post-hoc ATDP. So we can consider ATDP is like a few epoch plug-in stage that can be applied after any differential privacy or non-differential privacy training. It scrubs memorized sensitive span while preserving model utility and reduces compute time by up to 90% compared to traditional long differential privacy fine-tuning. So to decide which tokens deserve more protection, we use SPACI, which is a popular open source natural language processing library. It can automatically detect a named entity in text, things like people's name, organization name, locations, and dates. We build on top of this capability to design 4 different masking levels. The first one is low entity. So it means we just only mask the basics, which is person's name, organization name, dates, and location. The second one is high entity. We only mask the all of the SPACI NER types, things like the time, money, and percentages. And next one is low contextual. Then we just mask proper nouns, pronouns, and the subject object of the sentence. The last one is the high contextual. Finally, we also mask verbs, predicates. So most of the sentence is hidden. So you can check the example on the right to see the progressive masking. And we also do a lightweight, which is 1% human sampling and large language model cross-check to catch the misses or over masking. This page shows the details of our method. which is adaptive token level differential privacy. You can see the main idea of our approach clearly illustrated. We apply different ways to sensitive and non-sensitive tokens within each record. Sensitive token get a full weight, which is 1, while non-sensitive token get a smaller weight. We code the 50-50 principle to calculate the weight of non-sensitive tokens, specifically choosing a weight that makes the sensitive and non-sensitive parts each contribute roughly 50% of the gradient energy initially. Importantly, our method still fully respect traditional differential privacy mechanics. We keep the same record level gradient clipping and add noise just as the standard DPSGD does. Thus, the privacy accounting remains purely record level differential privacy. And we also designed a noise schedule that increased noise in non-constant increments with periodic resets. This aligns closely with our goal. We just want to quickly remove the model's memorization of sensitive tokens within a few epochs while preserving its original utility. Early on, we just use large noise value increases noise in non-constant increments to prevent model adaptation, thus enhancing forgetting of sensitive tokens. The periodic resets ensures noise does not increase excessively, protecting the model's core capability for being damaged. This page shows the experiment setup we use to evaluate our method. We use two datasets, which is Wikitext2 and ABCD. For models, we choose GPT-2 small with 124 million parameter and GPT-2 medium. And we compared our method against several baselines. The first one is no DP. So it is just the fine tuning on the full data without any privacy protection. And the second one is redirected. We just first mask sensitive span, then fine tuning on the redirected text. After that is just fine tune twice, which is GFD. They just first fine tuning on redirected data and then fine tuning again with differential privacy on the original data. This was the previous state of art. And after that, we have the standard baseline, which is the DPSGD, where uniform noise is added to all samples. Finally, we have our ATDP methods. So our method can be applied as a post hoc phase on top of any of the above, adding token weighted differential privacy protection. And for evaluation, we look at the two main metrics. The first one is validation perplexity, where lower is better. The second one is calorie exposure, which measures how much the model memorizes injected sensitive strings. Lower exposure means stronger privacy. To better evaluate our method's ability to remove sensitive information, we adopted mixed calorie scenarios during fine-tuning in phase 1. Aiming to maximize the model's memorization of calories. In phase 2, we switched to a non-mixed calorie scenario to test our capability to effectively reduce calorie exposure. So overall, this setup allows us to measure both privacy protection and model utility, and to see how our ATDP methods compares with the previous work. This slide highlights the key results of our method, ATDP on Wikitext2 with GPT-2 small. I want to emphasize not only privacy and utility, but also compute efficiency. First, in terms of privacy, ATDP really lowers the exposure. For example, if we add ATDP on top of the GFT, the exposure dropped from 28 all the way down to almost zero. That's already very close to random guessing. Second, it works fast. Just a few extra epochs of ATDP are enough to scramble memorized strings. Third, the utility is preserved. The validation perplexity basically stays the same as before ATDP, so it means the model still performs well. And the most important part is about compute, which is here means a relative computation time. So you can see the GFT by itself takes around 40 relative compute because it fine-tuned the model twice. But with redirected plus ATDP, you can reach almost the same exposure level with only 2.6 compute. That's about 10% of GFT's costs. And if you still want to combine GFT with ATDP, you can get even lower exposure, but just a small extra compute cost. So the big picture here is ATDP doesn't just give a better privacy, it also saves a lot of compute. You can get a really good level privacy protection at only a fraction of the training cost. So on this slide, we directly show how the model behaves differently for sensitive versus non-sensitive tokens across ATDP training. The orange line tracks sentence marked as sensitive. So you can clearly see the perplexity increasing significantly as training progresses. This increase indicates that the model is successfully forgetting or scrubbing this memorized sensitive token. In contrast, the yellow line represents sentences marked as non-sensitive. Here, perplexity remains largely stable across the checkpoints. This means the model maintains its original understanding and performance on non-sensitive content. So together, this demonstrates our methods effectiveness at targeted forgetting sensitive information is effectively removed without damaging the model's general capability. We also analyze how our method affects more model utility under different privacy detection tiers. So in this table, you can see each group represents a detector tier: low entity, high entity, and low contextual. The column labeled PCT shows the percentage of tokens flagged as sensitive. Also, we compare the validation perplexity at a matched calorie exposure level across methods. As you can see clear, our method, which is no DP fine-tuning plus ATDP fine-tuning, consistently achieves the lowest perplexity in every tier. This confirms that ATDP effectively preserve the model original utility, even as we enhance sensitive token protection. So to summarize, our proposed ATDP achieves targeted privacy protection by selectively reweighting token gradients. This allows us to effectively remove sensitive token memorization without losing valuable non-sensitive context. So in our experiments, ATDP consistently provided the best utility at matched privacy levels, meaning we reached a lower validation perplexity than other differential privacy methods at the same calorie exposure. Another key advantage is ATDP achieves the state-of-the-art privacy protection with only around 10% of the compute needed by traditional differential privacy fine-tuning methods. Finally, it's flexible and easy to integrate. So ATDP works as a lightweight plug-and-play step. You can add after any existing differential privacy or non-differential privacy training pipeline, making it practical for real-world deployment. But our method also has some limitations needed to be resolved in the future work. The first is scaling our method to full parameter differential privacy fine-tuning on very large large model is challenging. So we only evaluated small to medium models, and how this translates to bigger models is unclear. The second one is DB training is really sensitive to the hyperparameter, so we don't know what the optimal combination of the hyperparameters now. The third one is the weighting theory, which is the 50-50 principle we use currently lacks solid theoretical guarantees. We need to explore this theoretically is natural next step. Last, the accuracy of our secret detector directly affects privacy. To avoid missed sensitive tokens, designing a more robust detector remains a critical goal for deployment. So that is all the content of my presentation. Thank you for listening. Any question?
Thank you very much. Okay, then that's deliverable. Manjiang, I will ask a quick question because we have time for a question.
Okay.
So you mentioned ATDP proposed to apply a large noise at early stage of the training.
Yeah.
Okay. So what are the other parameters? Okay, let me put the question in this way. So have you done a kind of a sensitivity analysis to understand how the noise scheduling parameters like time and other parameters affected on the performance of the model and also the privacy?
You mean for the epsilon?
Yeah, epsilon and whatever other parameters.
Okay. So basically, the other hyperparameter, we just follow the.
No, I'm asking about the noise scheduling parameters because you said adding large noise early would be better.
Yeah.
So what are those type of parameters in terms of noise scheduling? And that's the first question. Have you done a kind of sensitive analysis to understand how they affected on the model performance and also the privacy?
Okay. Thank you for your question. So basically, because we apply the larger noise in the initial steps, so besides of the noise multiplier, this parameter, all other parameters, we just follow the previous work, which is the work we compared. And also for the for this difference for this different detector tiers, we do the sensitivity analysis because you can see that our method is a plug in the NoDP fine tuning. So actually here we breaks the differential privacy guarantee. So we don't compare the privacy budget here, which is epsilon. So but we will compare the privacy protection level by the calorie exposure. So that is the here the content, the method we evaluate the model's privacy preservation capabilities, because our method just plug in the NoDP fine tuning. Together they breaks the differential privacy, so we cannot compare the privacy budget, which is epsilon here. But we can also use the calorie exposure to evaluate the model's privacy preservation capability.
Good. Any other questions? Okay, no more questions from the audience, Manjiang. So thanks again for your presentation. Plus, thanks for the speaker once again.
Thank you. Thank you for listening.
Thank you.